April 12, 1943. Heat shimmers rise from the Tunisian sand. Major Robert Hendricks stands beside a disabled Sherman tank, its engine silent, transmission locked. He is a United States Army Ordnance officer, and he faces a problem that threatens to cripple the Allied advance across North Africa. The Sherman tank represents American industrial might. Factories in Detroit produce them by the thousands. Ships carry them across the Atlantic. But here in Tunisia, they die not from German shells, but from sand. Hendricks watches as mechanics drain thick, contaminated oil from the transmission housing. The gears inside are scored and seized. This tank has been in theater for 6 days. Hendricks carries a notebook filled with failure reports. In the past month, transmission breakdowns have disabled more Shermans than enemy action. Entire armored companies sit immobilized behind the front lines. The pattern is consistent. Tanks arrive from the depot. They move into position. Within a week, the transmissions fail. The cause is always the same. Sand has entered the sealed housing and mixed with the lubricant, creating an abrasive paste that destroys the gears. The problem is not new. Engineers in Detroit designed the Sherman for European conditions: rain, mud, paved roads. They did not anticipate the fine dust of North Africa. Every movement kicks up clouds that penetrate every gap and seal. The transmission breather system, designed to equalize pressure, becomes a pathway for contamination. The standard lubricant, adequate in temperate climates, breaks down in temperatures exceeding 120 degrees Fahrenheit. The maintenance schedule, written for garrison conditions, does not account for combat operations in desert environments. Hendricks understands the strategic implications. The Allied plan depends on mobile warfare. Fast-moving armored columns must outflank German defensive positions. Without reliable tanks, the offensive stalls. General Patton's Second Corps and Montgomery's Eighth Army both report the same crisis. Supply officers calculate that at current failure rates, half the Sherman force will be immobilized within 2 weeks. On April 15th, Hendricks begins his investigation at a forward repair depot near Teburg. Mechanics work under canvas shelters, surrounded by disabled tanks. He interviews sergeants who have torn down dozens of failed transmissions. They show him the evidence: sand packed into gear teeth, bearings worn to metal, oil that has lost all lubricating properties. One sergeant, a former automotive engineer from Michigan, explains the failure mechanism. The breather allows air to move in and out as the transmission heats and cools, but it has no effective filter. Sand enters with every breath. Hendricks examines the breather design. It is a simple valve mounted on top of the transmission housing, elegant for its intended purpose, fatal in desert conditions. He sketches modifications in his notebook: a longer tube, multiple filter stages, a reservoir to trap particles. But he knows that design changes take months to implement through official channels. He needs a solution that can be applied immediately to tanks already in the field. That evening, Hendricks meets with Lieutenant Colonel James Morrison, the Corps Ordnance Officer. Morrison is skeptical. The Army has procedures for equipment modifications, testing protocols, approval chains. Hendricks argues that they do not have time for normal procedures. Morrison asks what happens if unauthorized modifications cause additional failures. Hendricks responds that they are already losing the tank force. Morrison gives him 1 week to develop a workable solution. Hendricks assembles a team: 2 mechanical engineers from the Ordnance Depot, 3 experienced tank mechanics, a chemical engineer from the Petroleum Supply Unit. They work from a requisitioned warehouse in Beja. Hendricks establishes the parameters. The solution must use available materials. It must be simple enough for field mechanics to implement. It must work immediately. The team divides the problem into 3 components. First, prevent sand from entering the transmission. Second, use lubricants that resist breakdown in extreme heat. Third, establish maintenance procedures that address desert conditions. Each component requires a different approach. For the breather system, they experiment with filters. Standard air filters are too restrictive. They create excessive back pressure. A mechanic suggests using multiple layers of fine mesh screen, spaced to create settling chambers. They test the design by running a transmission on a test stand while blowing sand-laden air across the breather. After 6 hours, they disassemble the transmission. The oil is clean. The modification works. The lubricant problem is more complex. Standard transmission oil thins at high temperatures, losing its ability to maintain a protective film between metal surfaces. The chemical engineer explains that they need oil with a higher viscosity index. He contacts the Petroleum Supply Depot at Oran. They have stocks of heavy-duty gear oil designed for industrial applications. It was shipped for use in port equipment. Hendricks requisitions 500 drums. On April 20th, they conduct field tests. 3 Sherman tanks receive the modified breather systems and new lubricant. They operate for 48 hours in combat conditions, moving across open desert, engaging in gunnery exercises. Each evening, mechanics inspect the transmissions. The oil remains clean. The gears show no unusual wear. Hendricks writes his report. The third component is maintenance protocol. Hendricks realizes that even with improved hardware, tanks will fail without proper procedures. He develops a systematic inspection schedule. Every 12 hours of operation, mechanics must check the breather system and clean the filters. Every 50 hours, they must drain and replace the transmission oil, regardless of its apparent condition. Every 100 hours, they must inspect the gears for wear. The schedule is aggressive. It requires more mechanics and more time, but it addresses the reality of desert operations. On April 23rd, Hendricks presents his program to Morrison and the division commanders. He brings data from the test tanks. He brings cost calculations. He brings training materials for the mechanics. The generals ask hard questions. Can the supply system deliver enough specialized lubricant? Can the maintenance schedule be implemented without reducing combat readiness? Hendricks has answers. The petroleum depot can supply sufficient oil. The maintenance can be performed during normal operational pauses. General Patton, present at the briefing, makes the decision. Implement the program immediately across all armored units. The next phase is implementation. Hendricks faces a challenge of scale. The Second Corps operates more than 400 Sherman tanks. Each tank needs the breather modification. Each crew needs training on the new maintenance procedures. Each forward depot needs stocks of the specialized lubricant. Hendricks has 2 weeks before the next major offensive. He establishes a training program. Senior mechanics from each battalion attend a 2-day course at the Beja Depot. They learn to install the modified breather systems. They learn to recognize signs of transmission stress. They learn the new maintenance schedule. Then they return to their units and train their crews. The knowledge spreads through the armored force. Supply presents another challenge. The specialized gear oil must reach forward depots across a front that stretches 200 miles. Hendricks coordinates with transportation officers. Trucks carry the oil forward, prioritizing units scheduled for the upcoming offensive. By May 1st, every armored battalion has sufficient stocks. The breather modifications require fabrication. Machine shops at the rear depots produce the filter assemblies. They work 24 hours a day. Hendricks establishes a distribution system. Each morning, trucks carry completed assemblies forward. Mechanics install them during routine maintenance periods. Within 10 days, 80% of the Sherman force has the modification. Results appear quickly. By the first week of May, transmission failure rates begin to decline. Hendricks tracks the numbers daily. Before the program, failures averaged 12 per day across the Corps. By May 7th, the rate drops to 5 per day. By May 14th, it falls to 3 per day. The reduction is 78%. More importantly, tanks remain operational. Armored battalions report full strength. On May 6th, the final Allied offensive in North Africa begins. The Second Corps attacks toward Bizerte. The Eighth Army advances on Tunis. The mobile striking power that Hendricks preserved proves decisive. Sherman tanks exploit breakthroughs, encircle German positions, cut supply lines. The maintenance program keeps them moving. Mechanics perform the 12-hour inspections during brief pauses. They change oil at forward positions. The transmissions hold. German forces in Tunisia surrender on May 13th. The North African campaign ends. Allied commanders credit the victory to many factors: air superiority, naval blockade, infantry courage, but the armored units provided the decisive mobility. And that mobility depended on tanks that worked. Hendricks does not witness the surrender. He is at a depot near Souk El Arba, training another group of mechanics. The war continues. Allied forces will invade Sicily in 2 months. The Sherman tanks will go with them. The lessons from Tunisia will go as well. In June, the Army Ordnance Department formally adopts Hendricks modifications. Engineers in Detroit redesign the breather system for production tanks. The specialized lubricant becomes standard issue for desert operations. The maintenance protocols are incorporated into field manuals. What began as an emergency measure becomes doctrine. Hendricks receives a Legion of Merit for his work. The citation credits him with preserving the operational capability of the armored force during a critical campaign. But the award does not capture the full scope of his achievement. He identified a systemic failure. He developed a comprehensive solution. He implemented it across an entire Army Corps under combat conditions. He did it in 4 weeks. The transmission crisis in North Africa reveals a fundamental truth about military operations. Technology alone does not win wars. Technology must be adapted to conditions. It must be maintained under stress. It must be supported by trained personnel and adequate supplies. Hendricks understood this. His solution addressed not just the mechanical problem, but the entire system required to keep tanks running in the desert. After the war, Hendricks returns to civilian life. He works as an automotive engineer in Ohio. He never speaks publicly about his wartime service, but his methods influence military maintenance doctrine for decades. The principle of systematic preventive maintenance, tailored to operational conditions, becomes standard across all mechanized forces. The modified Sherman tanks continue fighting through Sicily, Italy, and eventually France. Some of them still carry the improvised breather systems that Hendricks' team fabricated in Tunisia. The specialized gear oil remains in use through the end of the war. The maintenance schedules, refined and updated, guide mechanics on every front. Major Robert Hendricks solved a crisis that threatened to immobilize the Allied armored force at a decisive moment. He did it not through dramatic action, but through systematic analysis, practical engineering, and effective implementation. His work saved hundreds of tanks. It preserved the mobility that won the North African campaign, and it established principles that kept Allied armor running through 3 more years of war. The solution was technical. The impact was strategic. The legacy endures.